What happens to old lithium-ion batteries when they are at the end of their lifetime? This is the question in our today's webinar, Recycling and Second Life Application for Lithium-ion Batteries. I welcome you, ladies and gentlemen, to our today's Fronius webinar. My name is Michael Raunig, and together with my colleague Christoph Schierlinger, we will guide you through this webinar today. Christoph and me are part of the trainings and education team here at Fronius International for the business unit Solar Energy. So when you have any questions during or after the webinar, please feel free to use our live chat function here in the GoToWebinar software and ask us all your questions that come to your mind. And of course, we will then answer your questions in the live chat or also after the webinar. So first of all, let's have a look what's on the agenda today. First of all, we will talk about the architecture and the chemistry of battery cells. So we will have a look about modern battery system designs. How is battery system design built up? What is the comparison of the cell chemistry? So this will also be a big part of today. The second big part is then the battery management. So the battery management system of each battery system. So this does the control and charging and discharging process of every system. This is very important, as well as thermal management of a battery cell. Last but not least, we will have a look on the battery managed system influence and on the cycle stability, so really on the lifetime of a battery system. The third part is then about the lifespan and the second life of a battery. So here we will take a closer look on second life scenarios and the field of application for battery systems. Last but not least, we will have a look about the recycling process. So first of all, let's start with the architecture and the chemistry of a battery cell. First to say, battery is not battery. So batteries differ a lot in their characteristics and features, and therefore every characteristic of a battery cell divides into three main parts. First of all, there is the cell chemistry. So the cell chemistry describes the active material that is used in the cell. So this is about the cell chemistry like we have, for example, with the NMC technology or with the lithium iron phosphate technology. We will come to the cell chemistry later on. The cell architecture, on the other hand side, describes the structure of the cell. So in this case, for example, the design, is it a cylindrical cell? Is it a pouch cell? And how is the cell itself built up? The battery management system is then a very important point to each battery system. So the battery management describes the control down to the cell level. So how is the battery cell controlled by the management system? And how is the controlling of the charging and discharging process done? These three parameters then decides the characteristic of each battery system. And therefore, within the characteristics, we gain a useful life. So this is the lifetime of the battery cell, the cycle stability, so the possible numbers of charging and discharging processes that are able, and the calendar aging. So the aging process on the cell level, this is just about aging of the cell itself. And last but not least, the C rate, so the capacity rate. This describes the possible charging and discharging power. So as you see, every manufacturer for battery cells has then to decide these characteristics of a battery system and then decides which cell chemistry, which architecture, and if he needs a battery management system for its application. This is also very important for choosing the right application for every battery system. First, about the cell architecture. There are three different main architectures that we have today in modern lithium-ion cells. First of all, we have the cylindrical cell. This is also called the round cell. This is the normal round cell that you know, for example, from different battery types. This was only also used in our Fronius solar battery system. Next up, we have the pouch cell. It is also called coffee bag cell because of its architecture. This is, for example, used in the LG Chem Reso system that you see in the middle picture. Third one is then the prismatic cell, and this looks like a little Lego stone, and this, for example, is used in the BYD battery box. So depending on the field of application and the needs that the battery manufacturer has for its system, he will choose one of these three cell architectures. Second up is then the battery system design. So let's have a look on how such a battery system is built up in the first place. We now take, for example, the BYD battery box. In this BYD box, we have 16 of these cells paired in series, and they are connected in series to one battery module. So 16 cells gain one battery module, and you can then connect up to 5, up to 9 modules to one battery system. Together with the connection area, with the battery management unit on top, this is the black part on top of it, that concludes in the overall battery system. In this case, for the BYD box, for example, there is used the cell chemistry. It is called the lithium iron phosphate, and it has a cell voltage of 3.2 volts and a cell capacity of 25 ampere hours per capacity. The module voltage gains then in 51.2 volts, and this is, so to say, the 16 cells in series. They are delivering my module voltage. The usable capacity, therefore, is about 1.28 kilowatt hours per module. So there you see how a battery system really is built up. Let's have a closer look now on the cell chemistry. And of course, the optimal, the best cell would have all the specific features at the highest specific rate. So for example, the best cell will have a very high specific energy, a very high specific power for charging and discharging, of course, a very high grade of safety, and of course also a performance and a good lifespan for a very long cycle life, and of course a very low cost point for making the battery system as cheap as possible. So in the real world, of course, this perfect battery cell isn't there yet, but there are lots of different cell chemistries available, and they have lots of different features and availabilities. So there are lots of different cell chemistry, as I mentioned, and I want to point out 3 specific cell chemistry that are now used on the market. So first of all, we have the lithium cobalt oxide chemistry. And this chemistry is often used in consumer electronics, like you know it from your smartphone, from your laptop, or from a table device. And this cell chemistry has a very high specific energy and has a very low cost point. And this is, of course, what you want for your smartphone battery. You want to have it a very high specific energy to bring your smartphone throughout the day. And of course, it should be at a very low cost point to make available a very low cost smartphone. On the other hand side, of course, there are disadvantages with this cell chemistry, like for example, the safety features or the lifespan. This is, of course, a very big main difference that we have, for example, from stationary PV battery storage systems. For stationary PV systems, there is often used the lithium iron phosphate technology. And this technology is very different from the other technologies because it has a very high safety standard and a very high lifespan. So with this technology, you can accomplish a very high cycle life and of course a very long lifetime for a stationary PV system. And this is, of course, especially the features that you want to make sure for your stationary PV storage, that you have a very long lifespan on the one hand side and a very high grade of safety. Because if you install the battery system in your basement, for example, you want to make sure that it's very safe. And this is a special factor about this lithium iron phosphate technology, that it is intrinsic safe. So that means that there is no chance of catching fire. And this lithium iron phosphate technology, for example, was used in our Fronius solar battery system and is nowadays used in the BYD battery box system, for example. On the other hand side, the downside is that the specific energy is a bit lower than the other systems, and therefore the system is a little bit heavier. But this doesn't make that much difference, because if you install the system in your basement, for example, it doesn't matter so much when the system is just some pounds heavier than another system would have. So therefore, this system is very good use for stationary PV storage. The third cell chemistry is then the NMC, the lithium nickel manganese cobalt oxide technology. So this NMC technology is very often used in electric cars, electric mobility. And this is because it has a very high specific energy and can deliver a higher amount of power. And of course, this is especially what you want for your electric car, because in a mobile application, you are limited in the space and also in the weight. So the electric car should be very light on the one hand side and should store a lot of energy for guaranteeing a very high range on the electric car. And therefore, this NMC technology, of course, is often used for electric cars, but also in a stationary sector, for example, with the LG Cam. The LG Cam uses this NMC technology, of course, because they have a correlation with the mobile sector, with the automotive sector. So as you see, there are lots of different cell chemistries, and depending on the application, the manufacturer will choose one of the specific cell chemistries. Second part is then the battery management for each system. So when it comes to battery management, we are always talking about the capacity of a cell. So in this case, for every cell, you have the so-called nominal capacity. This is the gross capacity that we are talking about. And there is now a possibility to block some capacity of every cell. So for example, there is a block capacity on top. This should prevent the overcharging of the cell. And then there is a so-called bricking protection. This should prevent the deep discharge of each cell. As you may know, battery cells, they don't like it when you charge them up to 100% and discharge them to 0%. And therefore, with these block capacities, we are gaining a usable capacity. So this is then the net capacity that the end customer can use of its battery. And this process is very important for battery cells because there is a fact about batteries that partial cycles increase the lifetime over proportional. So that means that when you charge your battery system, not always from 0 to 100%, but instead charge it from example 20% up to 80%, then you will gain a much longer battery life than you would have by charging and discharging it completely every time. So this stands in no comparison, because if you charge it only partial every time, you will get a much longer lifetime. And this is exactly what the manufacturer can do with the battery management system. So let's compare this now with the DOD value. The DOD value is called the depth of discharge, and this defines the charging percentage that you can charge and discharge your battery. So first example, we have a smartphone battery with a DOD of 100%. And there you see your smartphone battery is charged from 0 to 100% in the evening. And then of course is discharged completely when the customer decides to use his phone to 0%. And this is very bad for the battery system and the battery life. Therefore, with a battery management system, for example, like we have in stationary systems, we can decide to only charge from, for example, 10% up to 90%, and then back again. So we are really using this usable capacity. And this battery management system is the case, for example, electric cars, for stationary battery systems. And this makes a lot of difference, for example, the lifetime of the battery. The third possibility is then the C rate. And the C rate describes the charging and discharging power that is possible with battery system. So in our example, we have a battery capacity of 10 kilowatt hours of capacity. And then if you apply this battery to a 1C rate, so the charging process will take place at 10 kilowatts of power. So this is then really the charging power. And theoretically, the time for charging or discharging 10 kilowatt hours of energy would take place of 1 hour time. If you now decide to charge or discharge the battery system at a higher rate, so for example at 2C, then we are talking about a charging power of 20 kilowatts. Therefore, the charging and discharging time goes into half, so we only need 30 minutes for charging or discharging. On the other hand side, you can lower the C rate to 0.5 Cs and therefore only have charging power of 5 kilowatt. So this C rate, this charging and discharging behavior, is very important also for the battery and also for the lifetime. On the one hand side, this means the bigger the battery, the higher the charging and discharging power is possible. So that you can see, for example, also again at the BYD battery, when you decide to install more modules, you will have a higher charging and discharging capability. On the other hand side, this means the bigger the battery, the less trails it is for the cells at the constant C rate. So when you talk about having a 10 kilowatt hour system and you have always 10 kilowatts of charging and discharging power, a doubled capacity would mean that there is just a longer lifetime because there is less stress made to the cells. So regarding these charging and discharging powers, you can really have an impact on lifetime of a battery. Next up is then the thermal management of a battery cell. And as you may know, of course, battery cells, they like normal temperatures around 10 up to 30 degrees of Celsius. So they don't like it when it gets too cold, but also don't like it when it gets too hot. So at the idle temperature, they will have 100% of their performance. When it now gets too cold, for example, around 0 degrees or the minus degrees, the inner resistance of the cells are rising. And therefore, of course, the performance and the chargeable capacity lowers down. Therefore, it is always important to make sure that the cells are at the perfect idle thermal state. So in this case, when we are talking about stationary PV systems, for example, stationary battery systems, we can make sure that the battery always has a perfect temperature rate. For example, when you install your stationary battery system in the basement of the house, you always have around 15 degrees of Celsius, for example. And this ensures that you always have the perfect performance of your battery system. Other hand side, if it gets too hot, of course, then there is also a power reduction for avoiding cell aging and cell damaging like thermal runaway. So therefore, in a mobile application, again, for example, when we have an electric car, it is mandatory to have a thermal management. So you then will heat up the cells or cool the cells depending on the ambient temperature and on the usage. So therefore, as you see, again, with stationary battery systems, we have a very big advantage here because they are always in an optimal thermal area. So what is now the battery management system influence on cycle stability? You will see now here a diagram about the cycle stability of different battery cells. So in this case, first of all, you see on the left bottom corner, you see notebook and smartphone batteries, for example. And there you see they have on one hand side a number of cycles around 300 up to 500 cycles and a very low cycle stability, a very low durability. And this is of course because of all the factors that we discussed before, that for example, stationary batteries or electric car batteries will have a much longer cycle life. This is on one hand side on the specific cell chemistry that we were talking before, and on the other hand side, of course, on the battery management system. So like charging and discharging, not completely, and for example, having a thermal system in it. And therefore, you get out of these battery cells a very high number of cycle stability, and this can be up to 5,000 cycles or more. In comparison to the smartphone battery, it will have only about 300 or 500 cycles. And this means, of course, most of you know your smartphone battery will have a battery life of about only 2 to 3 years. In comparison to that, a stationary battery system or electric car battery system will have a lot longer battery life and therefore, for example, outlast the application that it is used for. So as you see, battery management is very, very important for the cycle stability and the lifetime. Next up is now, of course, the lifespan and the second life application. So now have a look on the influencing factors of the lifetime itself. So first of all, we have, of course, the battery aging. And of course, the battery aging is deployed under two different variants. First of all, we have the cycle stability. And the cycle stability describes the aging by usage. So all the factors that influence the usage, like dependent on the cell chemistry, the DOD factor, the depth of discharge, if I use partial cycles, or for example, what C rate is applicable, and of course the operating temperatures. These factors, they play into the field of the cycle stability. So this defines how many cycles I can drive with one battery system. On the other hand side, we have the calendar aging, and this describes the aging over time. So this is mostly depending on the cell chemistry that is used, and of course also on the ambient temperature and the increase of the temperature during the usage. So these two factors are then gaining into the battery aging, defining the battery aging of the cell. So what's now about durability of batteries? So in the recent years, we have a long-term experience, and they give, of course, new insights. So lots of batteries are out there for a long time, especially stationary battery system or electric car systems. And these new insights give manufacturers the possibility of guaranteeing long warranties for their systems. So for example, when we have it with 5 up to 10 years of warranty, and for example, in the automotive sector, 100,000 kilometers up to 240,000 kilometers, and a specific capacity of 70 up to 80% of rest capacity that should be there at the end of the lifetime. So as you see, manufacturers are giving lots and lots of warranties, and they are really relying on their battery systems because they know it will last a very long time. So for example, I have two possibilities of automotive applications here. We have the Volkswagen e-Golf that has a warranty of 8 years or 160,000 kilometers down to 70% of capacity. And for example, BMW is rewinding their warranty from 100,000 kilometers. They are extending this rate up to 160,000 kilometers. This is just because the manufacturers, they are seeing that the battery systems are lasting longer than they thought before, and therefore they are giving more and more extended warranties. On the stationary side, for example, we have the LG Chem Reso system, and this has a warranty of about 10 years or a defined energy throughput down to 80% of the nominal capacity. So as you see, warranty situation is very good for battery systems because they are lasting out long. But what happens now when the battery reaches the end of the lifetime? So first of all, I have brought to you the second life scenario for batteries. And best possibility here is, for example, a battery system that is used in its first life as an automotive battery. So this battery is then used in the automotive sector for an electric car application, for example, until it reaches its end of the first life. So let's say this is the end of the lifetime of the car. After some years, the car, of course, has reached its end of a lifetime. And then we talk about the end of the first life. After that, of course, especially with modern electric cars, they have a capacity of up to 60 or 70 kilowatt hours of power. This battery is not dead then. And in this case, there is the possibility to use it as a second life battery. And the second life battery can then be operated for some more recent years to operate, for example, stationary energy usage. So for example, using it as a PV system battery, for example, or storing wind power in it. Of course, nothing lasts forever, and therefore also the second life application will come to an end, and then we talk about the end of the second life. And after that, we have the recycling or remanufacturing process. So as you see, a battery is not dead after the usage in the car. It can be used at a longer pace. So I have brought to you two fields of application for second life usage. And of course, they are always used for grid stabilization and for backup power. So making sure, for example, that you don't exceed the grid voltage and the grid power that is drawn from the grid. And therefore, for example, one big example here is the Amsterdam Arena. And in this Amsterdam Arena, there is the battery used of pre-series Nissan Leaf cars. So these batteries are then built in the Amsterdam Arena, and they are used, for example, for storing the PV power that is produced during the day and then operating the lights of the arena during a play game, for example, play day. The second application is the BMW plant in Leipzig. And here you see there are lots and lots of BMW i3 car batteries used. So this was the pre-series of the BMW i3. And these batteries are then used for stationary purposes in a second life application. So as you see, these batteries are not disposal, but they are used in a second life scenario. And of course, there are lots and lots of more application fields for second life scenarios. So what happens then after the second life? Of course, after the second life, the battery still isn't disposal, so you won't throw it to some lift, but you need to recycle it because there are lots of valuable resources in a battery system. So for recycling a battery system, of course, it is mandatory to define it to the module scale and to the cycle scale. And then, for example, give it to a recycling process for giving back the most valuable resources. There are like lithium, cobalt, nickel, or manganese. And of course, this is a very important process because this recycling process ensures that this raw material can be again used for a first life application. So with this raw material, it is then possible again to manufacture a new battery cell again. And this cycle stability, this cycle recycling process is very important for ensuring a good cycle of the batteries. I have one example for the recycling process. This is, for example, in Bremerhaven in Germany. And there is a recycling plant that has a capacity of 10,000 tons per year. This company is called Redux, and they are recycling lithium ion battery cells already. As you may mention, the tons of capacity, the tons of battery cells, that is not here already because most electric cars, of course, still have their first life, and also application from stationary battery systems, they are still in operation and maybe used as a second life scenario. But of course, in the future, it is very important that more and more of these recycling processes are lifted further on and developed further on. But with this in mind, it is possible to really ensure a good recycling process for lithium-ion battery cells. Okay, so let's sum this all up. First of all, batteries are different. As we mentioned in the webinar, the lifetime of a battery depends firstly on the cell chemistry and of course on the DOD value, the depth of discharge. Furthermore, the C rate, so how you make the charging and discharging power of a system, is very important for the lifetime. Last but not least, the temperature and thermal management is very important. And as you know, of course, these three features, these three components can be done with the BMS, with the battery management system. So as you see, this battery management system is of course very important for stationary battery systems, for electric car battery systems. Unfortunately, there are no mobile devices. And this is of course also for you as an installer a very big argument when a customer says to you, my smartphone battery lasts only for 2 or 3 years. And the same will be with the stationary battery system. Then you can say, no, we have a battery management system with, for example, the Fronius Gen 24 Plus and the BYD battery box. And this battery management system, together with the cell chemistry of the BYD battery, ensures that you have a very long lifetime of the battery system. So overall, maybe a little sentence that you can remember is that battery is not battery. So you can't compare a smartphone battery with a stationary battery system or that is built in an electric car. Okay, if you want to get further information about our PV systems, of course, please make sure to check out our homepage, fronius.com. Under the download section, you can find further information on commissioning, for example, on our hybrid inverter and battery storage systems. Of course, I want to invite you to visit one of our storage and energy management trainings one day in the future. Of course, you can find informations and actual informations about fronius.com under the info centers. If you want to watch more webinars or how-to videos, you can find them on our YouTube channel and also, of course, on our website, fronius.com. Okay, so I think we have gained a lot of questions from you guys during the webinar. And I now want to ask my colleague, Christoph, to read out some informations for you.
Yeah, so actually, Michael, I think you did such a good job presenting this webinar or this topic that there are not so many questions right away. It was really good presented. But just to pick out one question I had so far, Michael, the question is, what do you think? Is there in the near future also a solution regarding vehicle to grid? Will there be such a solution? Is this economically? What do you think about that?
Of course, vehicle to grid is a very big topic also for us, and we also wish that vehicle to grid comes into production one day. But unfortunately for now, this is still away from the series production. So vehicle to grid is of course always depending on the car manufacturer. So depending on the car manufacturers, he has to enable this vehicle to grid situation. And of course, what you have to keep in mind, the mobile application, the electric car, is not there every time. So if you go with your car to work during the day, you are not able to store the PV surplus energy, for example, in your electric vehicle. But nevertheless, of course, vehicle to grid application is a very important topic, but unfortunately it will take some time already before it comes to market. And since then, of course, best field of application is the stationary battery system, like we have, for example, with the BYD battery.
Yeah. Okay. Thank you for that answer. Now we get some questions, but I think at this time here, I will just say we try to answer as much as possible now off the microphone via the chat. But don't worry, you will get the recording and the presentation of today's webinar after a few days, after we cut the recording to your email address, sent to this email address, so you can rewatch it. And if there are still any questions left, just send them through.
Yeah, thank you so much for listening today. Thank you so much for your presentation today. And of course, we would like to welcome you in one of our future webinars and future online trainings. Thank you for listening. Thank you for attention to today. And as always, see you soon. All the best to you. See you soon here at Fronius. Goodbye.